Far from the warmth of familiar stars, the universe spreads out as a nearly uniform sea of faint light, and in that quiet immensity, astronomers learn to trust patterns. Galaxies cluster along invisible threads, background radiation glows with near-perfect smoothness, and equations describe how matter and energy should weave together over billions of years. For a long time, the large-scale picture seems almost comfortingly simple. In this view, space is not an endless chaos, but a vast average where any region of the cosmos looks more or less like any other if one zooms out far enough. Telescopes gather light spectrographs, split that light into delicate rainbows, and computer plots reveal arcs and filaments that fit neatly inside carefully built theories. Then, without warning, a gap appears. It begins not as a dramatic revelation, but as a small absence in a crowded chart, a place where galaxies ought to be and simply are not. In the late 20th century, teams mapping the cosmos in 3 dimensions expect to see distant galaxies arranged like a mist of lanterns receding into darkness. Instead, they find a hollow. At first, it can be dismissed as noise in the measurements, a faulty detector, a misplaced decimal in a catalog of redshifts. The instruments are checked, the data reprocessed, the surveys widened. The hollow does not shrink. It grows. Each new observation pushes on its boundaries, hoping to find the missing structures hiding just beyond the edge, and each time the border moves outward like a receding tide. Where theory predicts a busy intersection of galaxy-filled filaments, reality reveals a cavern in the cosmic web, an expanse so empty that familiar language struggles to capture it. The numbers tell their own story, even when stripped of emotion. Light from this region has been traveling toward Earth for hundreds of millions of years. The volume it encloses spans hundreds of millions of light years in every direction. Statistical models say that a space that large, chosen at random, should host thousands of galaxies, perhaps even more if one includes dim dwarfs and irregulars that are usually missed in shallow surveys. Instead, there are only a few dozen scattered systems, lonely spirals and faint smudges adrift in what looks on a map like a wound in the universe. Astronomers eventually give this region a name that sounds almost playful at first, and then increasingly unsettling as its scale sinks in. It becomes known as the Boötes Void, the great nothing, a bubble of near emptiness located roughly 700 million light years from the Milky Way in the direction of the constellation called Boötes. The term supervoid is not poetic but technical, reserved for those rare cavities in the cosmic web that dwarf ordinary hollows. Yet even among supervoids, this one stands apart. Its radius is so large that light would take hundreds of millions of years to cross from one side to the other. Its interior density is so low that more than 99% of the galaxies expected there are simply missing. The surrounding universe, meanwhile, appears almost overbuilt with massive superclusters of galaxies piled along the edge of the void like glowing cities around a dark sea. In graduate lecture halls and conference halls, the Boötes supervoid begins as a curiosity, a footnote in presentations about large-scale structure. It is an outlier, an unusually empty patch that gently tests the limits of existing models. Over time, however, as surveys grow deeper and computers grow more capable, the void refuses to retreat into the realm of statistical flukes. Instead, it sharpens. Simulations of cosmic evolution seeded with tiny random density ripples produce voids of many sizes, yet voids that rival the Boötes supervoid remain extremely rare or fail to form at all within the available cosmic time. The equations that once felt so secure now carry a faint tremor of doubt. Somewhere between initial conditions and present-day structure, something may be missing. The emptiness itself becomes a kind of data. Observers measure not only where galaxies are, but where they are not, and begin to treat the absence of matter as carefully as its presence. The Boötes supervoid turns from a blank spot into a puzzle piece, its very nothingness implying a history of forces and flows. Space that empty does not arise casually. It must be sculpted by gravity expansion, and perhaps something more elusive over nearly the entire lifetime of the universe. Beneath the quiet images and smooth contour plots lies a deeper unease. The void is not merely large, it is oddly shaped, almost too simple in its symmetry, bordered by walls of galaxies, whose collective arrangement hints at a boundary rather than a mere gap. The discovery forces a subtle shift in perspective. Cosmology is no longer the story of a universe that is the same everywhere, perturbed only by small ripples. It becomes the story of a cosmos that can host enormous regions where almost nothing has happened for billions of years, and of a single dark sphere whose existence whispers that there might be chapters in the history of space and time that current theories have not yet learned to tell. For those who stare longest at the maps, the Boötes supervoid ceases to be just an absence and becomes a presence of a different kind, a silent question hanging in the background of every equation, asking whether the universe has been hiding a more intricate design inside what once seemed like simple, well-behaved emptiness. Robert Kirshner sits under the dim glow of red control room lights at the University of Michigan, surrounded by the quiet hum of instruments that translate distant starlight into strings of numbers. Night after night, the observing program repeats the same careful dance. A telescope collects faint photons from galaxies so far away that their light left before complex life took hold on Earth detectors register each arrival, and computers convert those signals into distances and speeds. The goal is to build a three-dimensional map of how galaxies are arranged around the Milky Way, a cosmic survey written not in hills and valleys, but in clusters and filaments of luminous matter stretched across hundreds of millions of light years. In this era, large surveys are still a relatively new experiment. Earlier generations of astronomers measured individual galaxies as special objects. Now, improved technology makes it possible to sweep wide regions of sky, compiling thousands of measurements that reveal how quickly each system recedes with the overall expansion of space. The pattern that should emerge is already broadly known from theory. On large scales, matter ought to be nearly uniform, sprinkled with modest overdensities that grow into clusters and superclusters, while underdense regions remain hollows rather than yawning chasms. When the early data begin to arrive, the plots look reassuringly familiar. Points marking galaxy positions cluster along curved structures, and empty spaces between those curves appear no larger than expected pockets left as gravity pulls matter together. Kirshner and his collaborators refine their selection criteria, extend their search volume, and slowly push deeper into cosmic distance. Somewhere within this growing map, however, a pattern of absence begins to take shape. At first, it hides inside the uncertainty, a region where only a few galaxies have been measured, and gaps can be dismissed as simple incompleteness. Yet the more data the team adds, the more stubborn the blank patch becomes. Each new observation that should have landed inside this zone instead appears just outside it, perched along an emerging boundary. What began as a hole no larger than others now looks different, larger, suspiciously coherent. A natural first suspect is the machinery itself. Telescopes mispoint, detectors drift, catalogs contain mislabeled entries. The team checks for errors that could carve artificial cavities into the survey. They verify that the instrument has observed the suspicious area as often as neighboring regions. They confirm that target selection has not accidentally skipped a swath of sky near the constellation called Boötes. They compare their measurements with independent catalogs. The void refuses to vanish. In the growing lattice of plotted points, the strange region now resembles a sphere of near emptiness embedded in a network of walls and filaments. Galaxy positions wrap around it like fog around a glass bubble. The more the team tries to catch it as a mirage, the more it solidifies into something that must be acknowledged. When Kirshner presents the result to colleagues, the reaction is cautious. Statistical flukes do happen. If enough volumes are studied, some of them will deviate from the average more strongly than simple models predict. Some voices suggest patience. Larger, deeper surveys will arrive. For the moment, the safest stance is to note the oddity and move on. Yet curiosity has a way of sharpening rather than fading when confronted with a puzzle that resists easy dismissal. Independent groups point their own instruments toward the same coordinates. Radio observatories scan for hydrogen emission from galaxies that might be too faint to appear in the original survey. Optical telescopes with wider fields attempt to fill the volume with fresh data. Each new campaign hopes to find the missing structures to reveal that the supposed void is merely a gap in human sampling rather than in the universe itself. Slowly, a different picture emerges. There are galaxies inside the region, but not many. A handful here, another there, often strung along suggestive alignments that slice through the volume rather than populate it evenly. When observers tally up the counts, the numbers fall drastically short of expectations. The density of galaxies inside this enormous bubble is only a small fraction of the cosmic average. Where thousands should crowd together over hundreds of millions of light years, only dozens appear. As the surveys grow and computer simulations improve, tension forms between theory and observation. Simulated universes that begin with smooth early conditions do grow voids, some quite large but truly gigantic cavities like the emerging Boötes supervoid remain rare, and when they appear they often lack the distinct boundaries implied by the data. Observers find that the real void's edge is surprisingly sharp, with galaxy density rising quickly at its boundary and massive superclusters draped like a shell around its perimeter. This combination of enormous size, extreme underdensity, and well-defined border transforms an odd patch of sky into a challenge. Either the universe is playing an extraordinary statistical trick, or there are aspects of cosmic evolution that standard calculations do not yet capture. In the quiet control rooms where the discovery unfolds, there is no sudden moment of revelation. Instead, there is the slow accumulation of unease as repeated checks fail to erase the same persistent absence. Over time, the Boötes supervoid becomes less a candidate error and more a new kind of object, a reminder that even in a cosmos largely described by elegant equations, there can still be places where those equations seem to hesitate, as if pausing on the brink of admitting that something about the grand pattern of matter and emptiness remains unexplained. On scales that dwarf clusters and individual galaxies, the universe reveals a hidden architecture. What looks at first like a random sprinkling of luminous islands turns under systematic mapping into a sprawling pattern that resembles a web frozen in mid-motion. Long filaments of galaxies thread across space, intersecting at swollen nodes, where superclusters form, while vast regions between those filaments hold far less matter than the average. Cosmologists call this arrangement the cosmic web, and within this web, ordinary voids are as common as the cells in a sponge. These voids are bubbles of lower density, often tens of millions of light years across, where galaxies are fewer and farther between. They are not absolute emptiness, but they are distinct enough that the transition from filament to hollow can be traced in surveys like the ones that first revealed the strange gulf in the direction of the constellation named Boötes. In most simulations, voids form naturally as gravity amplifies tiny ripples in the matter distribution left over from the earliest moments after the Big Bang. Slightly denser regions pull material in and grow into filaments and clusters, while slightly less dense regions are left behind, gradually evacuated as matter flows outward. Even so, these modeled voids tend to have modest sizes. Many measure on the order of a few tens of millions of light years, and only the most extreme stretch to around 200 million light years across. In that context, the Boötes supervoid stands out like a cavern inside a field of hollows. At an estimated diameter of roughly 330 million light years, its scale pushes far beyond what simple models comfortably allow. In a volume that large theoretical calculations say that thousands of galaxies should be present from bright spirals down to faint dwarfs, observations instead reveal only around 60 systems. The emptiness is therefore not mild but extreme. In terms of galaxy counts, more than 99% of the expected population is gone. Translating that sparseness into human imagery requires metaphor. If a typical part of the cosmos is likened to a great metropolitan region filled with countless cities and towns scattered across continents, then the Boötes supervoid resembles a continent-sized wilderness containing only a handful of isolated settlements separated by distances so vast that no ordinary traveler ever passes between them. It is not merely that there is extra room between galaxies, it is that the underlying scaffolding of the cosmic web appears to thin almost to nothing inside this immense volume, where one would expect to see filaments weaving through simulations produce subtle gradients and gentle bridges, yet the real maps show only a ghost of such structure, a faint suggestion of a tube of galaxies threading the middle and little else. Distances involved are so far beyond instinct that even astronomers accustomed to large numbers must pause. Light which circles Earth many times in a single second would take about 100,000 years to cross the Milky Way from one side to the other. To traverse the diameter of the Boötes supervoid, that same light would need to travel for roughly 3,300 times longer. Every photon that arrives from the few lonely galaxies found inside has been in flight for hundreds of millions of years, crossing a realm where encounters with matter are vanishingly rare. The scale alone would make the supervoid impressive. The combination of scale and depth elevates it to something stranger. Statistical studies ask how likely it is for a random universe resembling the best current models to produce a cavity of this size and sharpness merely by chance. Many analyses conclude that such a feature lies in the far tail of probability, a low likelihood event that ought to be rare in the observable volume. Nevertheless, there it is occupying a measurable fraction of the sky, its edges traced by enormous neighboring superclusters with names like Hercules, Corona Borealis, and Boötes itself. When these bounding structures are mapped, they form an almost spherical shell around the void, as though the cosmic web has drawn a circle around a forbidden zone. This geometric regularity is unsettling because nature on these scales usually prefers irregular forms. Superclusters often appear stretched, knotted, and twisted, the result of billions of years of uneven gravitational tugging. Voids, too, in simulations tend to be elongated and lumpy, more like distorted soap bubbles than perfect spheres. Yet the Boötes supervoid is remarkably round when the positions of its enclosing walls are plotted, and that roundness fuels a sense that something about its history may differ from the simple story of average underdensity growing quietly with time. For some cosmologists, the supervoid becomes a test of the principle that the universe is the same everywhere on the largest scales. If one region can host such a dramatic deviation, perhaps others do as well, and the large-scale smoothness once assumed as a background condition must be reconsidered. For others, it is a rare but natural fluctuation, remarkable in detail, yet still a legitimate child of known physics. Between these views lies a zone of uncertainty where data and theory have not yet fully met. The Boötes supervoid occupies that zone. It is large enough to strain expectations, but not impossible enough to demand an immediate rewriting of fundamental laws. It sits instead like a riddle carved into the connective tissue of the cosmos, hinting that the way emptiness assembles itself may hold secrets as profound as those contained in the brightest clusters and the most luminous galaxies. In standard cosmological stories, the universe begins in near uniformity. Tiny variations in density, far too small to see, in ordinary images imprint themselves on the relic glow of the early cosmos, a faint background of microwave light that fills all of space. These minute ripples in matter and radiation provide the seeds from which later structure grows. Where there is slightly more matter, gravity pulls a little harder, drawing in more material and slowly amplifying the initial contrast. Where there is slightly less matter, gravity pulls more weakly, and material drifts away toward neighboring peaks. Over billions of years, this simple rule sculpts the cosmic web, turning a nearly featureless beginning into a universe filled with filaments, clusters, and voids. When researchers attempt to fold the Boötes supervoid into this framework, they start from those first ripples. They ask what kind of initial underdensity would be required in the first few 100,000 years after the Big Bang for a region hundreds of millions of light years across to end up so empty in the present. The answer is unsettling. The initial deficit would need to be much larger than typical fluctuations, an unlikely valley in the early density field. In computer experiments, physicists generate many such initial conditions and allow them to evolve under the influence of gravity and cosmic expansion. Void-like regions do emerge, some large, but the path from modest random ripples to a chasm on the scale of the Boötes supervoid remains difficult to trace. The universe has an estimated age of about 13.8 billion years. From the era when matter first decouples from radiation and begins to fall freely under its own gravity, there are only a limited number of cosmic epochs in which structures can assemble before expansion spreads matter too thin. To empty out a region as large as the Boötes supervoid purely by matter flowing away along surrounding filaments, models indicate that more time would be helpful than the universe actually offers. The mismatch is large enough that cosmologists cannot easily ignore it. One possible escape is to imagine that the initial underdensity in this region was not merely a little below average, but extraordinarily so, granting gravity a head start in the race to evacuate matter. Yet that leads to its own problem because the statistics of the early universe read from the mottled pattern of the cosmic background suggest that such extreme features should be very rare. Another idea is that what looks like a single gargantuan void may have grown from the merger of several smaller voids. In that picture, many modest hollows formed close together in the early web, each expanding as surrounding filaments drew material away. Over billions of years, they could have merged like bubbles in a slowly rising dough, coalescing into a larger cavity. This scenario can produce big voids in simulations, and it offers a way to explain the faint tube of galaxies that appears to slice through the Boötes supervoid as if marking where different bubbles once pressed together. However, the details remain stubborn. When multiple voids merge in realistic models, their combined shapes tend to be irregular and scarred by residual structures. The Boötes supervoid, in contrast, presents a smoother, more spherical outline than such a merger would predict. Its edge is also unusually well defined, with neighboring superclusters forming a near continuous wall. The time available since the Big Bang, the scale of the void, and the crispness of its boundary together form a triangle of constraints that standard growth alone struggles to satisfy. Some researchers look to dark energy, the component that seems to drive the accelerated expansion of the cosmos, for help. Perhaps regions that begin slightly underdense experience a more vigorous local expansion as dark energy's repulsive effect faces less resistance from matter. In that case, voids could grow faster than models with uniform expansion assume reaching larger sizes within the same cosmic time. Yet measurements of many voids, including the Boötes supervoid, indicate that their growth broadly tracks the general expansion rather than leaping ahead. Dark energy, as far as current data reveal, behaves like a nearly uniform property of space itself. Others ask whether gravity itself might differ on the largest scales from the familiar form given by general relativity if the law that tells matter how to curve space-time and tells space-time how to guide matter changes subtly over hundreds of millions of light-years. Voids might grow in ways that current equations do not foresee. Modified gravity theories have been crafted that produce somewhat larger and emptier voids, but they must also match precise tests within galaxies and within the solar system. So far, every attempt to bend gravity on cosmic scales without breaking it on smaller ones faces severe tension with observation. As each possibility is examined and found wanting, or at least incomplete, the Boötes supervoid retains its awkward status. It is not so impossible as to shatter the framework of cosmology, yet it resists being tucked comfortably into that framework without special pleading. The time it seems to demand the early conditions it appears to require, and the smoothness of its present shape suggest a history that may involve something more than an ordinary patch of low density evolving quietly in a universe that otherwise follows simple rules. It stands as a quiet reminder that the narrative from primordial ripples to present-day structure, while compelling, may still lack certain chapters, and that within those missing pages the story of how such an immense reservoir of almost nothing came to be may hold clues to physics not yet fully understood. Seen not as a patch of missing points on a graph, but as a three-dimensional object, the Boötes supervoid resembles a hollow sphere nested inside a crowded universe. Its center lies roughly 700 million light-years from the Milky Way, but its influence on the surrounding pattern of galaxies extends much farther. When astronomers map the positions of the brightest clusters and superclusters around it, they find that many of the largest congregations of galaxies in that region lie near a common distance from the void's center, as if arranged along the inner surface of a shell. Names that already carry weight in large-scale structure studies begin to gather at the edges of the same volume. The Hercules supercluster, the Corona Borealis supercluster, the Boötes supercluster, and other massive formations appear to ring the emptiness their thousand galaxy cities, forming luminous walls around the dark interior. This configuration raises a subtle but persistent question. Did the walls produce the hollow, or did the hollow shape the walls? In the standard growth picture, superclusters emerge where the initial density is slightly higher than average, and matter has had time to collapse along intersecting filaments. Voids in this view are simply what remains between these growth centers, the spaces cleared out as material falls inward. If so, the Boötes supervoid would be a byproduct of the surrounding giants, a region evacuated because the gravitational pull of its neighbors was especially efficient. The alternative is that the region began unusually empty, and that its expanding underdensity pushed material outward, concentrating galaxies into a shell as the universe evolved. Both scenarios leave similar footprints in rough outline, but the details differ in ways that precise measurements can, in principle, distinguish. Observers look closely at the motions of galaxies near the void's edges. Each galaxy carries a recession velocity from the general expansion of space, but layered on top of that is a smaller motion caused by local gravitational fields. If the walls are pulling matter out of the void, galaxies near the boundary should show subtle drifts toward the superclusters. If the void itself acts like an underdense bubble, the pattern of deviations can take a different form, with motions reflecting a gentle push away from the low-density center toward denser surroundings. Data suggests that galaxies at the boundary do not fall inward to fill the hollow. Instead, they tend to move in ways consistent with being carried along by the overall expansion, with an additional component that often points away from the void. In simple language, the empty region does not seem to heal. It seems to maintain and perhaps slowly enlarge its absence as cosmic time rolls on. The shape of the boundary adds another layer to the mystery. Real structures born of natural processes almost never achieve perfect symmetry. Planets bulge at their equators, stars dimple and flare, clusters twist under the influence of infalling matter. Yet the Boötes supervoid, when described by the surfaces that best fit its galaxy, rich walls approaches a sphere more closely than many would expect. It is not mathematically perfect, but its deviations from roundness are modest given its immense scale. Simulated voids produced in computer universes of similar age and overall composition almost always show more distortion stretched along one axis, where neighboring clusters pull harder, and flattened in regions where filaments intrude. The Boötes hollow, by contrast, often plots as a remarkably simple bubble. Some cosmologists caution that this impression may be sharpened by selection effects. Surveys are deeper and more complete in some directions than others, and the supervoid's true outline could be more irregular than current maps imply. Even so, the tendency toward a clean spherical description persists through refinements. If this geometry is real, it demands explanation. Symmetry in physics usually signals either an underlying principle or a long history of processes that average away irregularities. For a star, spherical shape reflects the balance between gravity pulling inward and pressure pushing outward. For a soap bubble, surface tension smooths away protrusions until only a sphere remains. For a void enclosed by clumpy walls of galaxies, no simple smoothing mechanism presents itself. Gravity does not pull emptiness into a ball. It pulls matter, and matter in this case is concentrated not at the center but around the edges. In some speculative models of the early universe, bubbles of different vacuum states form and expand their boundaries, marking transitions where the properties of space itself change slightly. Such bubbles can be highly symmetric and can sweep out large underdense regions as they grow, compressing matter into shells. If an event of this kind had occurred in the distant past, the Boötes supervoid and its encircling superclusters might be fossil remnants of that expansion. Yet such models also predict other signatures in the cosmic background light and in the statistics of faraway structures that have not been clearly seen. Without these additional clues, the idea remains an intriguing but unproven sketch. More conservative explanations retreat to probability. In a universe with many voids and many boundary walls, a few will by chance line up to approximate spherical symmetry more closely than the rest. The Boötes supervoid may simply be the most spherical of many remarkable but not miraculous Between these interpretations stretches a quiet tension. The geometry of the void, its walls and their combined motion continues to act as a test, inviting ever more detailed surveys to trace the line where bright matter ends and the great nothing begins, and to ask whether that line is an accident or the outline of a process in the universe that has not yet been fully named. Within the broad near emptiness of the Boötes supervoid, the most striking feature is not the lack of galaxies, but the presence of a few that refuse to disappear. When the first surveys mapped the hollow, only a tiny handful of systems appeared within its boundaries, scattered so thinly that they almost blended into the background noise. As instruments improved and deeper observations accumulated, that count rose, eventually settling at about 60 known galaxies inside a space that by all expectations should host thousands. These survivors do not fill the void like scattered dust. Many of them trace a rough line through the darkness, a narrow corridor of light that runs across the interior like a faint thread through a vast glass sphere. Astronomers describe this structure as a filament or tube, a ghostly echo of the dense cosmic web outside, stretched until only a few luminous knots remain. The existence of this internal strand adds a new layer to the puzzle. If the Boötes supervoid were simply a region where little matter ever gathered, the few galaxies inside might be expected to lie wherever small early fluctuations allowed them to form, sprinkled without clear pattern. The appearance of a recognizable alignment suggests a more complex history. In one picture, multiple smaller voids may have expanded and merged their boundaries, initially crowded with galaxies. Where two such bubbles touched a sheet of matter would briefly separate them. As the voids coalesced into a single larger cavity, galaxies stuck on that former boundary could be left behind in a line or tube, a relic of surfaces that no longer exist, but once carved the region into smaller hollows. Observers probe the internal galaxies, carefully expecting that a life spent in almost total isolation would imprint itself on their shapes and histories. Standard models of galaxy evolution emphasize encounters and mergers. In crowded regions, gravity pulls galaxies together, distorts their disks, and kindles bursts of star formation as gas clouds collide. Over billions of years, these events gradually transform galaxies, thickening their central bulges and scrambling delicate spiral arms. In a supervoid, such encounters should be rare. Galaxies drift for tens of millions of light years without passing close to a neighbor. Without frequent tidal nudges, their structures ought to evolve more gently, perhaps preserving traits that are erased quickly in denser environments. Yet many of the known void galaxies appear disconcertingly ordinary. Some are neat spirals with well-defined arms and bright central regions. Others are smooth ellipticals or irregular systems that would not look out of place in clusters. Their spectra show mixed populations of old and young stars. Their gas content is not obviously exotic. It is as though they have followed the same broad evolutionary paths as their cousins in crowded regions, despite inhabiting an almost deserted province. This normality is in itself an anomaly. If isolation truly mattered as much as theory suggests, these galaxies should bear clear signatures of their quiet surroundings. Instead, their ordinariness implies that galaxies are more self-regulated than expected, capable of shaping their own evolution through internal processes, even when external influences are minimal. One especially intriguing inhabitant of the void is a graceful spiral often highlighted as an unusually lonely galaxy. Images from large telescopes show symmetric arms curling from a luminous core and star-forming regions glowing along the pattern. It lies in the supervoid with no substantial companions for tens of millions of light years in any direction, an island of light adrift in darkness. The internal filament of 60 galaxies thus serves two roles at once. Dynamically, it is a marker of how matter moved while the void was forming a fossil trace of earlier flows and mergers that turned modest hollows into a single immense cavity. Astrophysically, it is a set of laboratories, each galaxy a test case for how structure forms and ages when the usual bustle of interactions is stripped away. The data collected so far hint that isolation changes less than expected, or at least that the pathways available to galaxies are more varied than a simple dependence on environment can capture. Still, small differences may be hiding beneath the broad similarities. Measurements of chemical abundances suggest that some void galaxies may have retained more of their original gas, converting it into stars more slowly over time. Their star formation histories can be stretched and smoothed, lacking the sharp burst triggered by violent encounters. As telescopes with higher sensitivity continue to peer into the Boötes supervoid, they may uncover further nuances that distinguish these isolated islands from the rest of the galactic population. For now, the image that emerges is quietly paradoxical. Inside one of the largest known hollows in the universe, where gravity has apparently failed to assemble the usual crowded tapestry of galaxies, a slender thread persists. Along it, a few dozen galaxies carry on with seemingly normal lives, forming stars rotating in their dark matter halos and shining into the darkness as though unaware of the abyss surrounding them. Their presence makes the void feel less like a simple absence and more like a deliberately drained space, one that somehow left a single tenuous bridge of matter intact. Whether that bridge is the accident of a complex merger history or the imprint of deeper physical processes remains an open question, winding like the filament itself through the heart of the great nothing. Imagine a civilization that arises not in a galaxy cluster or along a bright filament of the cosmic web, but in one of the 60 galaxies that hang inside the Boötes supervoid. Its stars burn, its planets turn, and its inhabitants build instruments and stories in the same slow way any intelligent species might, but the backdrop is different. The night sky above their world is dominated by their own galaxy, a river of light that stretches from horizon to horizon. Billions of stars paint an arch overhead, dust lanes, cut dark paths through the glow, and nebulae hang like faint clouds along the galactic plane. Beyond that luminous disk, however, deep darkness waits, where observers on Earth look beyond the Milky Way and see faint smudges of companion galaxies and the mottled background of innumerable unresolved systems. The observers in a void galaxy would see almost nothing at all. Their unaided eyes would find no nearby spirals or irregulars to hint at an extended cosmic community. To them, the universe would appear to end at the edges of their own system of stars. For long ages, this isolation might shape their understanding of reality. Thinkers would build models of the cosmos in which a single galaxy is the entire stage. Myths would tie creation to the bright band of the home disk and treat the darkness beyond as a boundary rather than a window. Sailors and wanderers would still navigate by local constellations, but they would have no faint extragalactic beacons to suggest that their island of light is one among many. When technology advances and the first telescopes appear, they would transform the known cosmos, but not in the way they once did on Earth. Instruments aimed at the galactic plane would reveal star clusters, gas clouds, and perhaps small satellite systems. Yet telescopes pointed away from the galaxy into the depths of the supervoid would find only deeper blackness. Where early terrestrial observers looked through their own galactic dust and discovered other galaxies as swirling islands in the dark void, based observers would face horizons that refused to yield new structures. Their first great cosmological revolution, the realization that their galaxy is not the entire universe, would arrive late. Only when technology reaches a far more advanced level would the next stage unfold. On some clear night, a deep exposure taken far from the galactic plane would reveal a tiny smudge, then another, each faint and separated from the next by empty sky. Analysis would show that these objects lie at distances of tens of millions of light years or more, their light stretched by cosmic expansion, and their apparent sizes minuscule. Slowly, the picture would shift. The universe would no longer consist solely of one majestic galaxy. It would include a sparse archipelago of others scattered through an ocean of nearly pure darkness. Maps would show that almost all of the detected external galaxies lie along a narrow corridor, the same delicate filament that terrestrial astronomers see slicing through the Boötes supervoid. Analysis would reveal that the density of galaxies around this civilization is far lower than expected in any model in which matter is roughly evenly distributed. At some point, perhaps many generations after the first faint external systems are found, an idea would crystallize. The observers are not simply in a quiet part of a typical universe. They are inside a structure, a cavity of enormous extent, with their galaxy and its few companions hanging near the middle. Further measurements would search for the boundary. By pushing telescopes to their limits, astronomers living in the void would begin to glimpse something that seems almost like a wall. In every direction, at a distance of hundreds of millions of light years, the sky would show a sudden increase in galaxy counts. Vast superclusters would appear as dense knots of light at the survey horizon, arranged around the central observers like a shell. The realization would be unsettling and transformative. Their home, once assumed to be at the center of everything, by absence of evidence to the contrary, would still be at the center, but now of an immense hollow surrounded by walls of matter. In this thought experiment, the psychological and scientific shock mirrors in reverse what terrestrial cosmologists experienced upon discovering the Boötes supervoid. Observers on Earth look outward from a relatively crowded region and find a great nothing beyond. Observers in a void would look outward from near perfect isolation and eventually discover that the greater universe is richly filled, but that they inhabit one of its rare empty chambers. For both perspectives, the supervoid becomes a stage on which ideas about typicality and centrality are tested. A species in a void galaxy could reasonably believe for a long time that the universe is mostly empty. A species in a dense cluster could equally reasonably believe that space is tightly woven with matter everywhere. Only by mapping beyond the immediate surroundings and by combining local data with models of cosmic evolution does the more complete picture emerge. In that wider picture, the Boötes supervoid is not an error or a special exemption to the rules, but part of the full spectrum of structures that arise from subtle beginnings. Yet its extreme emptiness and the way it would cradle an entire civilization in apparent solitude give it a special narrative resonance. It stands as a reminder that where a sentient culture happens to arise in the cosmic web will strongly shape its early stories about the universe, and that only persistent, careful observation can reveal when those stories have been written inside a bubble of extraordinary silence. Physical emptiness is never truly empty. Even in the spaces between galaxies and normal regions of the universe, thin gas drifts individual atoms separated by distances that would seem immense on planetary scales. Stray photons wander in from every direction. Magnetic fields thread the dark with invisible lines of force. In clusters, hot plasma fills intergalactic space, shining in X-ray light and buffeted by shock fronts from supernovae and active galactic nuclei. Against this backdrop, the Boötes Void stands out not only as a deficit of galaxies, but as a place where almost all of the usual clutter has thinned to a whisper. Counting galaxies is only the first step. Astronomers also probe the gas in and around the void, searching for the faint signatures of hydrogen that betray the presence of intergalactic medium. Radio surveys tuned to the characteristic emission of neutral hydrogen find far less signal inside the supervoid than outside. Where typical cosmic volumes show a gentle haze of gas, the void appears nearly transparent. The number of atoms per unit volume drops to levels that approach the limits of what instruments can detect. In practical terms, this means that a photon entering the void from one of the surrounding walls can travel for hundreds of millions of light years without encountering a single atom to scatter from or a dust grain to absorb its energy. In laboratory terms, the void is a vacuum greater than any the technology can produce. Even the best engineered chambers on Earth still contain billions of particles in each cubic centimeter. The vast, dark interior of the Boötes supervoid contains perhaps only a handful. Neutrinos, the nearly massless particles that stream from stars and supernovae, already pass through ordinary matter with ease, slipping through entire planets as though they were transparent. Inside the supervoid, their journey becomes almost perfectly unimpeded. Trillions of neutrinos cross the cavity every second, tracing paths from distant galaxies and clusters, yet their chance of interacting with anything inside the void is so small as to be effectively zero. They enter, cross, and exit as if moving through mathematical nothing, carrying with them information about their origins, unchanged by the intervening space. This extreme emptiness gives the void a peculiar status as a kind of natural conduit. In normal cosmic regions, light and particles gradually accumulate the marks of their passage. Photons scatter off electrons, changing direction and losing coherence. Charged particles spiral along magnetic field lines, their paths twisted and blurred. Over millions of years, these interactions add noise to any signal that tries to travel across great distances. Inside the Boötes, supervoid by contrast, signals face almost no obstacles. A beam of light sent from one wall to the opposite side would fan out geometrically but would otherwise arrive essentially unaltered even after 330 million years of travel. Patterns encoded in its intensity or polarization would survive as faithfully as the finite speed of light allows. It is as though the universe carved out a colossal laboratory for testing how well information can persist when the usual sources of interference are stripped away. From a theoretical perspective, such an environment is also an opportunity to probe deeper questions about the nature of vacuum itself. Quantum theory says that even perfect emptiness is alive with activity on very small scales, with pairs of virtual particles flickering in and out of existence. These fluctuations give rise to subtle effects such as tiny shifts in energy levels and forces between objects placed close together. Measuring such phenomena in terrestrial laboratories is difficult because real experimental spaces are filled with many competing influences. In principle, the interior of a supervoid offers a cleaner stage. over scales of hundreds of millions of light years, any slight deviation from expected behavior in the propagation of light or high-energy particles could reveal new properties of the quantum vacuum or constraints on exotic physics. For now, the idea remains mostly conceptual because no instrument can yet span such distances in a controlled way. Nevertheless, cosmologists consider the void when designing strategies to test theories that predict minute changes in the speed of light, the behavior of neutrinos, or the possible interaction of dark matter with itself. The emptiness also has gravitational consequences that are not immediately intuitive. While massive clusters and filaments bend light, strongly acting as lenses that magnify or distort background galaxies, underdense regions act as negative lenses. Light passing through a void can arrive slightly dimmer or shifted in angle compared to what it would do in a perfectly uniform universe. By measuring these subtle effects across many lines of sight, astronomers can reconstruct the distribution of mass, both visible and dark, within and around the Boötes supervoid. The result confirms that not only normal matter but also dark matter is depleted there. The gravitational potential inside the void is shallower than average, meaning that objects within are less strongly held and more easily carried outward by the overall expansion of space. In this sense, the void functions like a hilltop in the landscape of cosmic density, where marbles placed near the crest slowly roll away toward valleys of greater mass. Over billions of years, this gentle sliding contributes to the continued evacuation of the region, reinforcing the almost pristine emptiness that current observations reveal. From the standpoint of cosmic evolution, the Boötes supervoid becomes a kind of reference zone, a place where processes that complicate structure elsewhere are minimized. There are few shocks from colliding gas clouds, few tidal disruptions, and few overlapping gravitational fields. The physics is not simpler in principle, but fewer competing influences operate at once. This makes the void an appealing natural laboratory for testing models of how dark energy shapes the expansion of space, how dark matter arranges itself when left mostly alone, and how quantum fluctuations imprint themselves on the largest accessible scales. In a universe where most places are busy with interactions, collisions, and overlapping signals, an enormous region where almost nothing happens stands out as an unexpected gift. It lets cosmologists glimpse how the universe behaves when many of the usual distractions have faded, and in that clarity, the emptiness itself becomes a source of data, a silent record of how far the cosmos can go in the direction of pure absence without ever truly reaching it. Information is fragile in most places. Messages carried by light and particles accumulate scars as they move, each scattering an interaction, adding a little blur, a little noise, a small step toward erasure. Inside the Boötes supervoid, that erosion slows almost to a halt. A photon launched from one of the massive superclusters on the boundary into the hollow interior begins a journey that will last for hundreds of millions of years. In a typical region of the cosmos, it might encounter gas dust and magnetic fields on the way, changing direction or losing energy in tiny increments. In the supervoid, the photon crosses distances so free of matter that it may never meet a single atom. Its path is shaped only by the large-scale curvature of space-time and the steady stretching of wavelengths caused by the expansion of the universe. Whatever pattern was imprinted on that light at its origin, whether it is the random glow of hot gas or the structured signal of a pulsed source, remains largely intact when it emerges at the far side. The same is true for high-energy cosmic rays and for neutrinos, whose ghost-like passage becomes almost perfectly ideal once they leave the denser outskirts and enter the cavity. From a human perspective, the timescales involved make such a channel seem unusable. No civilization lasts for hundreds of millions of years in any currently known story, and no experiment on Earth can wait that long for results. Yet the universe itself has no such limitation. It has already been sending its own natural beams across the supervoid since long before Earth formed. Every supernova that detonates in a surrounding wall floods the interior with neutrinos that will sweep through in straight lines, preserving records of their birth conditions with exquisite fidelity. Every burst of radiation from a quasar or a flaring black hole at the boundary writes a bright, brief script into the void, a script that will still be legible when that light finally reaches a distant cluster on the other side. If such natural broadcasts can survive, then in principle artificial ones could as well. It becomes possible, at least in imagination, to picture the void as a link between eras of the universe that never overlap locally. A beam transmitted from one side today would not arrive at the opposite wall until long after any particular star, planet, or species has come and gone. By the time the message emerged, the entire configuration of galaxies on the receiving side might have changed. Clusters could have merged, stars could have burned out, and new civilizations, if any arise, would be the heirs of many forgotten cycles. The void, in this sense, is not a conduit for conventional communication, but a medium for messages cast into the deep future like bottles released into a slow-moving cosmic ocean. The same property that makes the Boötes supervoid a playground for thought experiments about far future communication also makes it a potential tool for probing extremely subtle physical effects. Many theories that try to extend or refine known physics predict that over very long distances and times, tiny deviations from the usual behavior of light or particles may add up. A minute energy dependence of the speed of light, for example, would be negligible over planetary scales, but could cause measurable differences in arrival times for photons of different energies crossing hundreds of millions of light years. Ordinary paths through the universe complicate such tests because scatterings and interactions along the way confound any signal. Paths through near-perfect emptiness like those available inside the supervoid offer cleaner baselines. If astronomers can identify events on opposite sides of the void whose emissions travel mainly through its interior, they can compare their detailed properties with those of similar events whose light has passed through more cluttered space. Any consistent discrepancies might hint at new physics. For now, the practical challenges are formidable. Observers must identify sources at just the right locations, measure their emissions with extreme precision, and disentangle the influence of gravitational fields from any other effects. Still, the mere existence of such an enormous, relatively undisturbed volume means that nature has already set up the stage on which these experiments could in principle be performed. Beneath these technical considerations lies a more speculative curiosity. If the void is such an excellent preserver of patterns, could it already be full of messages that no one has learned how to read? Cosmic rays and neutrinos that cross it today may carry imprints of processes in distant galaxies that occurred before life on Earth began their detailed distributions, encoding histories of star formation, black hole growth, and even exotic events in the early universe. To current instruments, these particles appear as diffuse background statistical fields that are described by average intensities and broad spectra. Perhaps hidden within those statistics are subtle structures, deviations from randomness, that when properly decoded will reveal new layers of order and phenomena long thought to be noise. Some thinkers stretch the idea further, entertaining the notion that an advanced civilization might someday use a void like Boötes as a canvas modulating natural particle fields to imprint durable signatures that can survive across cosmological times. Such scenarios remain deep in the realm of conjecture, unanchored by direct evidence, yet they underscore how the supervoid reframes the relationship between distance, time, and information. In most contexts, separation spells decay. Signals weaken, patterns blur, and meaning dissolves. Inside this immense hollow separation still weakens, but does not necessarily corrupt. Patterns can endure across spans that would otherwise erase them. In that endurance, the Boötes supervoid quietly links events that are in every other respect separated by ages and by unbridgeable stretches of space, turning the largest known chasm of near nothing into one of the universe's most faithful, if slowest, recorders. Dark energy enters the story of the Boötes supervoid as a quiet background that explains the behavior of space but not the origin of the hollow itself. Decades after the first galaxy maps revealed the Gulf observations of distant supernovae show that the expansion of the universe is speeding up instead of slowing under gravity. To account for this, cosmologists introduce dark energy, a smooth component that seems to fill every region and exert a gentle repulsive influence. In the simplest description, it does not clump, does not form its own structures, and does not distinguish between crowded clusters and near empty voids. If that picture is right, then the Boötes supervoid is not a bubble of concentrated dark energy. It is an unusually thin patch of matter suspended in the same accelerating space-time as everything else, precisely because so little mass lives inside. However, the motions of galaxies at its edge provide an unusually clear view of how gravity and expansion work together in a universe dominated by this unseen pressure. Astronomers trace those motions by measuring the positions and redshifts of galaxies in and around the void, building three-dimensional maps that include both its interior and the surrounding superclusters. Each redshift records how much the wavelength of light has been stretched by cosmic expansion since it left its source, and from that stretching one can reconstruct a distance. Superposed on the global expansion are smaller peculiar velocities caused by the local pattern of mass. Galaxies on the luminous walls of Hercules, Corona Borealis, and Boötes feel the pull of those dense regions, but they also respond to the underdense space beneath them. If dark energy is smooth and constant, theory predicts a specific pattern of flows. Matter should drift gently away from the void's center toward denser surroundings, and the void should grow at almost exactly the same rate as the universe as a whole. If instead dark energy varied from place to place or coupled differently to matter in emptier zones, the pattern of velocities around Boötes would shift subtly, allowing the hollow to expand faster or slower than expected. To push the test further, researchers turn to an older light, the cosmic microwave background that fills all of space with the faint afterglow of the Big Bang. As those ancient photons cross the evolving cosmic web, they gain and lose tiny amounts of energy while climbing into and out of gravitational wells and hills. A large underdense region like the Boötes supervoid slightly modifies this journey. Photons passing through spend more time in a shallower gravitational potential and emerge a little less energetic than they would have in a perfectly uniform universe, leaving a barely cooler patch on the microwave sky. By comparing the measured size and depth of Boötes with the amplitude of any associated cool spot, cosmologists test their models of structure growth and of how dark energy influences the large-scale gravitational landscape. Calculations show that a void with the observed properties of Boötes should imprint only a very subtle feature barely above the level of random temperature ripples imprinted at the dawn of cosmic time, and that result quietly rules out more dramatic ideas in which voids like this sculpt the microwave background in ways far stronger than the data allow. Reconstructed velocity fields show no such dramatic deviation. Within present uncertainties, galaxies around the Boötes supervoid move just as they would in the simplest models of a universe filled with cold, dark matter and a smooth, dark energy. The hollow region grows because space everywhere grows, but it does not balloon in any special way. Its walls do not rush outward as though pushed by an extra repulsive force, and its interior does not appear shielded from the acceleration that acts elsewhere. There is no clear sign that dark energy is more concentrated there, nor that it has been drained away. To the best of current measurements, the mysterious component that shapes the fate of the cosmos behaves with indifferent uniformity, treating the largest known underdensity much as it treats any other region. For many cosmologists, this is quietly reassuring. A dark energy that behaves like a cosmological constant already fits a wide range of observations, and the Boötes supervoid, rather than overturning that picture, seems to support it. Seen in the light of this conclusion, the supervoid offers a glimpse of the universe's distant future. In a cosmos where dark energy remains constant, accelerated expansion continues without end. Structures that are bound tightly by their own gravity will stay together, but those that are not will drift irreversibly apart. Over immense spans of time, the cosmic web thins, filaments stretch, and gaps between islands of matter widen. Regions that resemble the Boötes supervoid, once rare, become common, and the rich pattern of superclusters that now ring the void fades into a more uniform solitude. In that sense, the hollow in Boötes is both a present-day oddity and a preview, a local example of the isolation toward which dark energy slowly carries everything. Yet the very smoothness that makes dark energy easy to describe also means it cannot by itself explain why this particular region is so empty. The unusual history of Boötes must lie in the details of its early conditions and in the slow play of gravity before acceleration took over, and in that respect the void remains not an answer but a question, a silent volume in which the rules of a smoothly expanding universe are obeyed, while the reasons for this extreme pocket of near nothingness remain just out of reach. In maps of the cosmic web, dark matter appears only indirectly inferred from how it pulls on things that can be seen. Galaxies trace its densest knots, gas warms where its gravity compresses it, and light bends around its invisible clumps. In regions as crowded as clusters, these signals overlap and complicate one another, making it hard to disentangle exactly how much dark matter lies where. The Boötes supervoid offers the opposite, a place where the usual tangle thins and the quiet makes it easier to listen for the subtle ways gravity acts when most of the mass has gone elsewhere. To chart the unseen structure in and around the void, astronomers turn to gravitational lensing. As light from distant background galaxies travels toward Earth, it passes through the large-scale distribution of matter on the way. Every concentration of mass, visible or dark, slightly deflects the light, making background galaxies appear minutely stretched or sheared. By measuring these minute distortions across wide fields of sky, cosmologists reconstruct a map of mass density, much as ripples on a pond surface can reveal the shapes of objects beneath. When this technique is applied to the region that includes the Boötes supervoid, the resulting mass map shows a clear depression where the galaxy deficit lies. The basin is broad and shallow, not empty, but markedly lower in mass than neighboring regions. The ratio of dark to normal matter inside appears similar to the cosmic average, but both components are reduced. In other words, the void did not form by selectively removing only luminous galaxies while leaving their dark scaffolding intact. It is a genuine underdensity in the full matter field. This finding quietly constrains many speculative ideas. If some exotic process had evacuated only gas and stars, perhaps through powerful feedback from ancient quasars, or the action of hypothetical repulsive fields that couple only to normal matter, the lensing signal would show a relatively normal dark matter distribution beneath the luminous deficit. Instead, the gravitational imprint mirrors the visible scarcity. Whatever carved the supervoid carved through both kinds of matter at once. The way dark matter drapes around the hollow is also revealing. Filaments visible in ordinary galaxy counts extend into the region only weakly, their dark counterparts forming faint bridges that correspond to the internal tube of about 60 galaxies. Around the outer walls, dark matter clusters strongly where the great superclusters sit, deepening the gravitational wells that host thousands of galaxies. Between the mass distribution smooths out, creating a gradual rise from the low plateau inside to the high ridges outside. Simulations tuned to match these features suggest that the void affects not just where galaxies can form, but how fast they move once they exist. Galaxies inside the hollow sit in an environment where gravitational pulls largely cancel out. There is no dominant nearby cluster tugging them strongly in one direction. Instead, they experience weak, nearly symmetric attractions toward the surrounding walls. Combined with the overall expansion of space, this produces motions that are almost pure Hubble flow with only slight deviations. In this sense, the interior galaxies behave like test particles in an almost ideal expanding universe. Their velocities become sensitive probes of how gravity and dark energy together shape the growth of structure. Analysts compare their observed motions with the predictions of different models of dark matter and gravity. The standard picture in which cold dark matter interacts only through gravity and general relativity governs the curvature of space-time at all scales reproduces the broad patterns well. Exotic alternatives that invoke self-interacting dark matter, long-range fifth forces, or large deviations from Einstein's equations tend to produce voids with either too much residual structure, too rapid an evacuation, or peculiar velocity fields that do not match the data around Boötes. In this way, the supervoid quietly rules out many imaginative theories that might otherwise escape notice in more complex environments. Yet there are hints, small and contested, that not everything lines up perfectly. Some reconstructions of galaxy motions around the void suggest slightly larger peculiar velocities than the simplest models predict, as though the underdensity were a little deeper, or the effective gravitational law a shade different on these enormous scales. The discrepancies sit near the edge of current uncertainties, where measurement errors, incomplete sky coverage, and biases in distance estimates can mimic or conceal real effects. Each new survey that revisits the region refines the numbers, sometimes shrinking the tension, sometimes shifting it, but never entirely erasing the possibility that the Boötes supervoid may be whispering about subtleties in gravity that are too faint to hear clearly elsewhere. The void also plays a role in tests that seek to compare how dark matter behaves in different cosmic environments. In clusters where it dominates the mass budget, dark matter seems to form dense cores and extended halos that align well with simulations. In filaments, its distribution is harder to map but broadly consistent with expectations. Inside voids, its presence is more diffuse, and the shapes of its sparse clumps can reveal whether it experiences forces beyond gravity. For instance, if dark matter particles occasionally collide with each other, they might avoid forming sharp edges at void boundaries, instead smoothing the transition. The relatively crisp edge of Boötes in both luminous and dark components argues against strong self-interaction. When all of these strands are woven together, an image emerges of the Boötes supervoid as a region where dark matter and gravity behave very much as the prevailing model says they should, yet push to an extreme. The underdensity is deeper and larger than most, but it still follows the same general rules. Dark matter flows away from low density toward high galaxies right along those flows, and dark energy stretches the whole pattern over time. If there are deviations from this simple story, they must be subtle, hiding in small mismatches between predicted and observed motions, or in tiny anomalies in lensing maps. The emptiness of the void does not scream new physics. It murmurs, inviting closer and closer scrutiny. In that sense, Boötes functions as both confirmation and question. It confirms that the scaffolding of invisible mass drawn by ordinary gravity and smoothed by cosmic expansion can generate astonishingly large hollows without shattering the underlying framework. At the same time, its sheer scale and near symmetry keep alive the possibility that somewhere in the fine print of how dark matter arranges itself, or how gravity propagates across hundreds of millions of light years, there are small departures from the familiar laws that have yet to be noticed. The supervoid waits its dark matter web drawn thin, offering itself as the clearest canvas upon which such departures, if they exist, might eventually be seen. Exotic explanations for the Boötes supervoid grow in the spaces where conventional models strain. Once observations confirm that the hollow is real, nearly spherical, deeply underdense, and ringed by superclusters, theorists begin to ask whether the familiar story of gravity amplifying small primordial ripples is the only possible route to such a structure. The first alternatives stay close to standard physics. One suggestion is that the region began as an unusually strong fluctuation in the early universe, a valley in the primordial density field deeper than the gentle hills and hollows traced by the cosmic microwave background. Quantum mechanics allows randomness in those initial conditions, and in principle nothing forbids a patch that is exceptionally underdense, as long as its occurrence is sufficiently improbable. In that picture, the Boötes supervoid is simply the most extreme outcome in a very large statistical game, a place where matter started out so scarce that even 13.8 billion years of evolution could not repair the deficit. The difficulty is that the statistics encoded in the background radiation do not obviously show such extreme valleys. The modeled pattern of slightly hotter and colder spots on that ancient sky is remarkably smooth. To embed a seed for Boötes inside it without disturbing that smoothness requires either careful tuning or more intricate initial conditions than the simplest inflationary models provide. Other ideas invoke relics from phase changes in the early cosmos. As the universe cooled from its initial hot state, the fields that govern fundamental forces may have shifted from one configuration to another, much as water freezes into ice. In many theories, such transitions can produce defects where regions of different states meet. Cosmic strings, thin filaments of extreme energy, or domain walls, sheet-like boundaries between distinct vacuum states are two examples. A network of such objects could in principle influence how matter later clusters, carving out underdense zones or compressing material into walls. If a large domain wall or a tangle of strings had passed through the area that became the Boötes supervoid, it might have swept away matter or inhibited its collection, leaving an unusually empty zone ringed by denser ridges. However, searches for the distinctive signatures of cosmic strings and domain walls in the cosmic microwave background and in gravitational lensing surveys have so far come up empty, and the upper limits on their abundance are tight. Any contribution they make to structure formation must therefore be modest. It is difficult to attribute a single large clean void solely to such rare defects, without also producing many other anomalies that are not seen. A more dramatic class of explanations looks beyond our universe entirely. In models of eternal inflation, space as a whole continues to undergo rapid expansion, while bubble-like regions where inflation has ended bud off and evolve as separate universes. Occasionally, two such bubbles may collide. At the moment of impact, energies are enormous, and the collision can rearrange matter and radiation along the contact surface. In some simulations, these encounters leave circular scars in the affected universe's regions, where the density of matter is lower or higher than average, and where the cosmic microwave background shows ring-like temperature patterns. It is tempting to imagine the Boötes supervoid as one such scar, a sphere carved by a grazing collision with another bubble universe in the distant past, its surrounding superclusters forming from matter swept up at the edge. If this were so, the void would be not just a statistical oddity, but evidence of physics beyond the cosmic horizon. Yet once again, the details are hard. Bubble collisions should leave correlated imprints in both large-scale structure and background radiation, and careful searches for the predicted patterns have not yielded decisive detections. Some faint hints have been reported and later reinterpreted as random fluctuations. At present, the multiverse explanation remains an alluring story rather than a conclusion, a way of framing the void as a message from outside rather than a quirk from within. A different strand of speculation focuses on the vacuum itself. In these models, dark energy is not a single, perfectly uniform ingredient, but can settle into slightly different states in different regions. A patch that slipped early into a state with marginally higher vacuum energy would experience stronger local acceleration, gently pushing matter outward and sharpening any initial underdensity into a broad, smooth hollow. Over billions of years, such a region could come to resemble a supervoid with an almost ideal spherical outline and very little structure inside. The challenge is that dark energy already appears remarkably even when measured across vast distances, and any variation strong enough to sculpt boots would have to hide within tight observational limits. After passing through this landscape of alternatives, one returns somewhat reluctantly to the possibility that the Boötes supervoid may indeed be a rare high-significance fluctuation in an otherwise well-described universe. Its existence would then be a reminder that even in a cosmos governed by simple statistical rules, extreme outliers can arise when the volume is large enough. Yet the door to more exotic origins does not fully close. The void's near-spherical symmetry, deep underdensity, and clean surrounding walls keep it near the boundary where improbable natural feature and subtle new physics meet. In that ambiguous space, cosmologists continue to test both conservative and far-reaching ideas, using the Great Hollow not only as a challenge to existing models, but as an invitation to imagine what other histories space and time might be capable of writing into the fabric of the cosmic web. In some corners of theoretical discussion, the Boötes supervoid becomes a canvas for audacious ideas, those that step beyond natural processes and ask what an intervention by intelligence on cosmic scales might look like. Imagine a civilization that has endured for tens or hundreds of millions of years, long enough to migrate beyond the fragile surfaces of planets and to reorganize entire stellar systems for its own purposes. The energy output of a single star already dwarfs anything a species can use on planetary scales. Structures envisioned to capture that energy, like shells or swarms of collectors around stars, would render those suns dim or invisible in ordinary light, re-radiating most of their power at lower temperatures. If many stars in a galaxy were enclosed in such constructs, the galaxy would gradually fade from view in visible wavelengths. If such engineering continued driven by demand for energy, or by a desire to control the local environment, the process could in principle extend from stars to entire galaxies. From the outside, that region would begin to look empty, even though mass remained. In this speculative picture, the Boötes supervoid is not an absence of galaxies, but a sphere where most galaxies have been transformed into something observationally dark. The roughly 60 visible systems inside would then be the exceptions, either too remote, too recent, or deliberately left untouched. The surrounding wall of superclusters would mark where this wave of transformation halted or has not yet reached. The near-spherical geometry would be a natural consequence of expansion from a central origin, with the front advancing at some fraction of the speed of light and maintaining a fairly smooth shape in the absence of strong external perturbations. Such an idea is dramatic, but it makes concrete, testable predictions. Galaxies that have been enclosed in vast energy harvesting structures should radiate waste heat at characteristic infrared wavelengths. Deep surveys of the Boötes region therefore search not only for the absence of visible light, but for an excess of smooth infrared glow that could indicate hidden activity. To date, observations reveal no such anomalous emission on the required scale. The interior of the void looks dark in infrared as well as in optical light, showing only the faint points expected from the known sparse galaxies. Either there is no such engineering, or it is accomplished with methods that suppress waste heat beyond what known physics allows. Furthermore, transforming thousands of galaxies within a region 330 million light-years across would require coordination across distances so vast that even a civilization using relativistic probes would need immense times to complete the work. Between the epoch when first galaxies formed and the era from which the void is now observed, only a few billion years have passed. There is barely enough time to send light speed signals from the center to the edge, let alone to deconstruct and rebuild entire galactic populations. These timing arguments weigh heavily against such an artificial origin, at least in the simple form of an expanding wave that has modified every galaxy it touches. Another strand of speculation imagines not a single directed project, but many separate civilizations all reaching similar technological stages and each enclosing their local stars and galaxies for their own reasons. If galaxies in one large region happen by coincidence to host an unusually high number of such cultures, the combined effect could dim that region as though a more unified effort had taken place. Yet this idea also faces difficulties. It still must explain why the pattern of dimming would track a nearly spherical volume so neatly, and why the edge of that volume would align with massive superclusters. A random scatter of advanced societies across the universe should produce a patchwork of partially dimmed areas, not one large clean bubble of near-nothingness. The lack of clear technosignatures in other studied regions compounds the problem. If a transformation of this scale were possible and common enough to have occurred in Boötes, hints of similar work might be expected elsewhere. For now, surveys find no convincing evidence that whole galaxies are being systematically enclosed in ways that current instruments can detect. Despite these objections, the artificial void scenario persists in the imagination because it clarifies the scale of the Boötes mystery. It highlights how demanding it would be to rearrange matter on such distances and in such a symmetric way. By asking what it would take for intelligence to carve out a supervoid, theorists gain a sharper sense of what natural processes must achieve if no such intelligence is involved. The thought experiment also flips the usual framing of cosmic isolation. In many stories, a great emptiness is a sign of neglect, a place where nothing has happened. In this speculative mirror, an emptiness as deep and clean as boots might be the aftermath of intense activity, a region harvested and tidied by beings whose motives and methods remain opaque. There is no observational requirement to adopt that view, and the weight of evidence still favors an origin rooted in early density fluctuations and long-term gravitational evolution. Yet the very fact that the Boötes supervoid can host such extreme thought experiments shows how far it sits from ordinary experience. It is an arena in which questions about the upper limits of engineering, the longevity of civilizations, and the detectability of intent on cosmic scales can be explored against the backdrop of an actual structure in the sky, even if the most conservative answer continues to be that this enormous, nearly empty sphere is the product of impersonal physics operating for billions of years with no guiding hand at all. Gravity, in the form first written down by Einstein, has passed every experimental test that laboratories, planets, and stars have offered. It describes how mass and energy bend space-time and how that curvature guides the motion of worlds and light. On the scales of solar systems and galaxies, its predictions agree with observation once dark matter is included. Yet the Boötes supervoid pushes this theory into a regime that is hard to probe elsewhere, where gravity operates over hundreds of millions of light years across a region that is almost devoid of matter. In such a place where the usual sources of curvature are thin to a trace, tiny deviations from the standard law could in principle become visible. That possibility has turned the supervoid into an arena where some of the boldest ideas about modified gravity and quantum effects in space-time are quietly tested against reality. In the simplest view, the void is an underdense patch that behaves like any other underdense patch, only on a grander scale. The matter distribution defines a gentle gravitational hill, and galaxies move in response, rolling away from the low point toward denser surroundings, while the entire landscape stretches under the influence of dark energy. Detailed reconstructions of these motions use redshift surveys to infer distances and velocities, then subtract the uniform expansion to reveal the smaller residual flows. When this is done for the region around Boötes, most of the pattern fits comfortably within expectations. Still, a few analyses hint at small mismatches. Peculiar velocities of some boundary galaxies appear slightly larger than naive models predict, as though the void were a shade deeper or the effective pull of gravity altered on these scales. The differences are modest near the edge of observational uncertainty, and they may yet vanish as data improve. For theorists interested in alternative forms of gravity, however, even such tentative hints are worth attention. Some proposed modifications suggest that the force law changes at very low densities, becoming marginally weaker or stronger than Einsteinian gravity when averaged over enormous volumes. In dense clusters, these effects would be masked by local fields. Inside a supervoid, they might shift how quickly matter drains away or how steep the gravitational hill becomes. If so, the exact size and depth of the Boötes supervoid, along with the way its edges curve, could carry the imprint of a law of gravity that is not quite what the standard equations assume. Another frontier lies where gravity meets quantum mechanics. A full theory of quantum gravity remains elusive, but many candidate models predict that space-time has a structure at very small scales that differs from the smooth continuum of classical relativity. Over the normal distances of astrophysics, such microscopic irregularities would average out. Over paths as long as the diameter of the Boötes supervoid, they could in principle accumulate into tiny observable effects like a barely perceptible blur in the image of a distant galaxy whose light has crossed the cavity. Searches for such signatures have so far come up empty, placing limits on how strong any quantum graininess of space-time can be. The fact that light from galaxies beyond the void arrives with sharp images and well-defined interference patterns tells observers that if space-time is foamy at the smallest scales, its roughness must be exceedingly fine. The center of the supervoid draws its own share of speculative gravity. In a pure underdensity, there is nothing special about the exact middle. It is simply the point most distant from surrounding mass. Yet symmetry invites questions. If some exotic object, such as a primordial black hole, naked singularity, or remnant of an early phase transition were lurking there, its gravitational influence would be spread over the entire cavity. Tiny additional curvature could slightly alter the motion of interior galaxies or the paths of light crossing the void. Astronomers have aimed everything from radio telescopes to X-ray observatories at the central coordinates looking for unusual emissions or lensing that might betray a hidden mass. Thus far, the center appears at least as empty as any other point inside, with no bright activity, no obvious compact object, and no strong local deformation of background galaxy shapes. This absence does not absolutely rule out exotic cores, but it pushes any such objects into ranges of mass and behavior that are increasingly contrived. As with many other lines of inquiry tied to Boötes gravity tests in and around the supervoid, end up supporting the prevailing framework while leaving just enough room at the margins for continued curiosity. General relativity, cold dark matter, and smooth dark energy together do a surprisingly good job of reproducing the broad features of the void when seeded with plausible early conditions. At the same time, the extremity of the underdensity ensures that any future deviation from these ideas, if it exists, is likely to show up more clearly here than in more typical environments. The Boötes supervoid, therefore, stands as a kind of natural interferometer for gravity, an enormous baseline across which space-time can reveal whether it truly behaves the same way in the loneliest expanses as it does near stars and planets. For now, the answer seems to be yes, but the very existence of so large and clean a test region encourages astronomers to keep asking the question, refining measurements, and listening for the faintest hints that somewhere between the bright walls and the dark heart of this cosmic hollow gravity might be preparing to say something new. After all the surveys, simulations, and speculative models, the Boötes supervoid remains less a solved problem than a steady presence in cosmology, a vast reminder that the universe still contains features that do not fit neatly inside familiar narratives. It sits in the sky as a region that can be mapped and quantified, yet each new layer of precision simply sharpens the outline of the question rather than erasing it. Observatories continue to gather data that trace its contours with ever finer detail. Redshift catalogs add more galaxies to the surrounding walls and refine the distances to the 60 or so lonely systems in the interior. Weak lensing measurements deepen the mass map, clarifying how dark matter slopes away from the center toward the superclusters. Each of these efforts tightens the range of what is allowed. Any explanation must account for an underdensity that is genuine and not an artifact of missing data for a near-spherical geometry that is more regular than typical voids in simulations, and for a history that has emptied both dark and luminous matter from a volume hundreds of millions of light-years across, without leaving obvious scars. At the same time, new instruments extend the search for comparable hollows elsewhere. Wide field surveys in visible light map galaxy distributions over vast swaths of sky, revealing networks of filaments and voids that stretch far beyond the local supercluster environment. Some of these newly charted voids approach the scale of Boötes, suggesting that extreme emptiness may be more common than once thought, though none yet match its combination of size, depth, and clean surrounding walls. Missions devoted to studying dark energy and dark matter treat voids as key laboratories. They count how many exist at each size, how they cluster, and how they imprint themselves on the background light. The statistics that emerge serve as another test of cosmological models. If there are more giants like Boötes than expected, then the early conditions or the laws that govern growth may need revision. If Boötes remains an outlier, attention shifts to the specific pattern of early ripples that might have seeded such a singular hollow. In theoretical work, the supervoid continues to act as a boundary condition. Models of inflation are checked against the requirement that they not produce too many regions with such extreme underdensities, yet allow that at least one exists. Proposals for exotic components or fields are weighed partly on whether they would leave additional signatures in and around Boötes that are not seen. Ideas about multiverse collisions, varying vacuum energies, or topological defects must thread a narrow path between boldness and the tight constraints that lensing maps, galaxy surveys, and microwave background observations now impose. The void does not rule these possibilities out entirely, but it provides a real structure against which their predictions can be measured, reducing the space of unconstrained speculation. For observers, perhaps the most striking aspect of the Boötes supervoid is how quietly it coexists with the rest of the universe. It does not distort the cosmic expansion dramatically, does not dominate the pattern of background temperatures, and does not host obvious anomalies in the properties of its few interior galaxies beyond their profound isolation. From the vantage point of a typical galaxy elsewhere, it is simply one patch among many an unusually deep dip in a field of fluctuations. Yet for those who live near enough and have instruments sensitive enough to trace three-dimensional structure on these scales, it becomes a focal point, a place where multiple lines of inquiry intersect. It links questions about the early universe to those about dark matter, dark energy, and even the possible role of intelligence on cosmic scales, not because it demands any one answer, but because its existence brushes against each of these themes. The future of its study will likely be incremental rather than dramatic. New surveys will refine its profile, narrow uncertainties in its size and depth, and perhaps reveal faint structures that current instruments miss. Better measurements of galaxy motions around its edges may either erase or confirm the small tensions that some analyses have hinted at. More sensitive lensing studies could detect subtler features in the dark matter distribution, placing stricter limits on any exotic physics that might operate differently in near emptiness. At the same time, searchers for life and technology elsewhere occasionally return to the thought experiment of civilizations inside such a void, imagining how their view of the cosmos would differ and whether their signals, if any, could be threading through this darkness even now unnoticed against the background of natural radiation. In the end, the Boötes supervoid may settle into the role of an extreme but natural structure, its rarity understood statistically, and its properties folded into a mature cosmological model. Or it may continue to resist full assimilation with one or another measured feature, staying just outside the range that simulations can reproduce without adjustment, serving as a constant prod toward more refined theories. Either way, it already fulfills a deeper function. It reminds anyone who studies it that even in a universe increasingly charted by precise instruments and powerful computers, there remain enormous regions where almost nothing has happened for billions of years, and that inside those regions the fabric of space and time may still be telling a story that current physics only partly understands. In that sense, the greatest hollow in the observable universe is not emptiness, but possibility, a vast silent room in which future observations and ideas will continue to echo slowly, filling the great nothing with meaning even as its darkness endures.